And so we're trying to figure out what is the age of the sun. Well, that's not an easy thing to do, to figure out how old the sun is. We know it's shining, but it's been shining pretty consistently for a long time. And so how do you tell how old it is? Well, if we could see down in the core, we would know, because at the beginning it's 90% hydrogen, but as the sun gets older, it uses up its hydrogen. So if it was half used up, we know it's halfway through its lifetime. Okay? And if it was 99% used up, then we know it'd be 99% through its 10 billion year lifetime. So, the truth is, we can't really do that because we can't see what's happening in the core. So, how do we figure out the age of the sun? Well, we realize that the sun and the whole solar system formed at the same time. We do that because we see everything spinning in a counterclockwise direction, all the planets lining in a plane. We see that what we did is we formed out of a cloud of dust and gas that was spinning counterclockwise. That formed the solar system. So if we get the age of the planets, then we get the age of the sun at the same time, because they're all formed together. And so that's what they did. They started looking at radioactive dating of rocks on the Earth, the oldest rocks they can find on the Earth, the oldest rocks they found on the Moon, the oldest rocks from meteorites, which are rocks that have fallen to the Earth from the solar system. And they looked for what is the oldest rock that we can figure, and they found out that the age of the sun in the solar system we estimate to be about 4.5 billion years. And it's very consistent, meaning that if you look at the oldest age of the moon rocks, they're at about 4.2 billion years. Oldest rocks found on the Earth, which were actually found in Greenland, are about 4.0 billion years. It took a little longer for the Earth to solidify because it's bigger than the moon. The oldest meteorites we found are about that same age too. And now we know exactly how the sun works. We can do computer models that simulate the sun. Take this giant ball of gas and it figures out, okay, if you have this much gas, what's the temperature, the pressure, what kind of reactions are going to occur, and we can run that simulation and get an estimated age. Now, it doesn't prove anything, but it helps us to believe we're right, because if they do the simulations, they get the same age of about 4.5 billion years. Okay? And so we're pretty sure that the sun is at about 4.5 billion years, so about halfway through its lifetime. So do we have to worry about the sun burning out? No, we got another 5.5 billion years from now. So put it on your really long range calendar. All right, so we know what the sun is made of, mostly hydrogen and helium. Now, if you go by mass, because a helium atom weighs a lot more than a hydrogen atom, right? It's 4 heliums to each one. This becomes 70%, 30%, and 1% everything else. I just want to tell you that because if you read your textbook or you read online somewhere, they may give you these numbers as opposed to these numbers. Doesn't mean they're wrong, it means they're just measuring it a different way. All right. So, let's talk about the interior of the sun. First of all, before we get to that, let's talk about why the sun is balanced. I mean, why is the sun not getting bigger or smaller? Stay in the same size. Well, in the sun, remember, in the center of the sun, in the core, we have thermonuclear fusion, which is turning hydrogen into helium. That's nuclear bomb. It's nuclear explosion. What does gas do when you explode it? It wants to expand outward. So it's trying to push the outer layers of the sun and the core. It wants to blow up. Okay? But we also have all this gas in the sun, and all the gas has gravity on it. So what we have is gravity's trying to crush the sun into a small ball, and the gas pressure is trying to push it out. So gravity is pulling the sun together. And gas pressure is pushing it out. Well, for the sun, and the good thing about the sun is that these two balance each other exactly, and we have a name for that. We call that hydrostatic equilibrium. That's the balance of gas pressure pushing out and gravity pulling in. All right, and the good thing is, for that 10 billion years, while the sun is converting hydrogen into helium in its core, it's in hydrostatic equilibrium. It's going to stay the same size and give off pretty much the same amount of energy all the time, which is really good for life on Earth. If you have a star that's very unstable, like it's really bright, faint, and changes all the time, life is a hard time existing in those conditions. Where we have a very nice, stable sun giving off the same amount of energy for billions of years, that allows life to exist on this planet. All right. In fact, what happens is, after 10 billion years, the core is now all helium, and so the core actually starts to collapse inward because the gas pressure is loose, and the outer layers actually get bigger, and the sun's going to expand. And the sun's going to expand outward and actually swallow up Mercury and Venus and get real close to the size of the Earth's orbit. Now, the Earth may not be inside the sun, but it's going to be burned to a crisp. So, yeah, by the time the sun's about to die, we got to move. All right, let's talk about the interior of the sun. We already talked about that in the center, in the core, is where all the energy is being produced. And we can't see down into the core. But what we find is the energy has to go from the core out to the outer surface, and then it has to go across space and get to us. Well, hopefully from some class somewhere, one of your physics classes, maybe a 9th grade science class or something, you learn that heat can be transferred one of 3 ways. You can do it by either radiation, which is photons, essentially, conduction, or convection. And those terms should sound familiar to you. What we find with the sun is the core, this is where all the energy is being produced. Remember, hydrogen and helium. But then how do you get that energy out to the outer layer? Well, this first layer here is called the radiative layer. And this layer means that the energy is actually being transported by photons. Remember, I told you that the core, when there's a nuclear explosion is giving off all kinds of gamma rays. But those gamma rays just run into the gas. And the gas that gets released here might be only several million degrees, so it gives off X-ray photons. And then as it gets further out, those get down to ultraviolet. And then by the time you get to the surface, it's giving off visible light. So the radiation, the photons, are transferring energy from here to here. But once you get to a point out here, about 2/3 of the way out, then it becomes more efficient for blobs of gas to transfer the matter by motion, which we call convection. This is the convective layer. So what happens in the convective layer is this hot gas, so this gas down here, remember it's hotter as you go in. That gas gets very hot, but instead of transferring by radiation, because that gas is hot, it starts to float up to the surface. The same principle behind a hot air balloon. You get the gas hot inside the balloon. The hotter gas is a lower density gas, and so that's going to make it rise through the atmosphere. Same thing here, you get this blob of hot gas. That blob of hot gas rises to the surface. When it gets to the surface here, it emits photons. We draw photons as squiggly lines coming out. Essentially, it emits visible light photons. Well, when it emits light, light is energy, so that's taking the energy away, and so this blob of gas then cools off, and once it gets colder, it's higher density, it falls back down. And so what we see is in the outer layers of the sun, these blobs of gas are churning. Blobs of gas are going down and coming up continuously, all the time. That's why the sun looks like this when taken through a filter. You see the lighter ones, the brighter ones? Brighter little dots here, we call this granulation. That's the hotter gas coming up. The darker pieces is the cooler gas falling down. So the whole sun is actually, the outer layer of the sun is churning. The inside is not, but the outer layer is churning. And it's mixing it up. Same principle when you have boiling. When something is boiling, it's showing convection too. You're taking heat from the bottom of the pan, and the blobs of gas turn into steam, and that steam rises up through the water, and when it gets to the surface, it releases the steam, cools it off, and the whole thing is just churning around. That's convection. Convection is very important on the Earth. Convection is what powers all our weather. Hurricanes, tornadoes, they're all powered by convection, by blobs of gas moving from one place to another, from higher density to lower density. We call it high pressure and low pressure regions. And so that's why we have weather. It also powers the ocean currents. So convection is very, very important in moving energy from one place to the other. All right. So, energy, just to review, energy here, we have 3 layers in the interior of the sun. So if I ask you for what are the layers, you say, well, we have a core, surrounding it's a radiative layer, the outer layer is a convective layer, and the convective layer is blobs of gas moving up and down. All right. Now, we're going to talk about the atmosphere of the sun. So I'm going to move this. So now we're going to do the sun's atmosphere. Now remember, the sun has no solid surface. So what do you call the surface when there's no ground or anything? We call our surface ground where you hit the ground, and then we have the atmosphere as the gas above it. Well, if it's all gas, then how do you call what